Hello everyone, I'm Francois Rheault. I'm a postdoc at Vanderbilt University under the supervision of Bennett Landman. Today I'm going to continue the intro to computational neuroanatomy. My goal in this presentation is simply to introduce the various concepts of the DIPY Workshop, the theme that will be occurring this week, and to provide context into the line of thought of diffusion MRI processing. So you already know that the modality of choice that we like here is the magnetic resonance imaging. So this is a modality that is amazing for brain investigation. So it provides amazing resolution, great contrast, and different kind of sequence that allow you to look at different types of tissue contrast. So, for example, if you want to look at the decrease or increase of volume structure, cortical thickness, lesion for multiple sclerosis or aging, if you want to look at early sign of stroke using diffusion-weighted image, white matter atrophy or disrupted network, all of these questions can be investigated using MRI, and it's just an amazing kind of modality. But in DIPY, we have a special love for the contrast that is diffusion MRI. So diffusion MRI encompasses a lot of different specific sequence, but we probably will talk specifically about linear and spherical only this week. It's important to know that there is some content about structural image. So there is a talk about tissue classification on T1 image, and deep learning segmentation for tumor case, I think. So these talks are specifically about structural image, but most talk will be about diffusion MRI itself. So if you have a question related to tissue segmentation, I'm sure this talk and the speaker can answer your question. So what I want to do today is just to give an idea of the line of thought that we have when we process diffusion MRI data. So you have an idea of what comes before what and what have an impact on the following step, just to give some context on the DIPY workshop as a whole. So diffusion MRI is the acquisition that aims to probe the microscopic movement of water. Microscopic imaging, microstructure imaging is the quantification of the tissue composition and their characteristic. Local modeling is an attempt to represent or simplify the fiber population orientation. So all the brain structure are locally oriented in the brain. Tractography is the act of reconstructing the microscopic structural connectivity. So reconstruction of probable paths that connect different regions. Connectomics is a simplified representation of a global structural connectivity signature. Bundle segmentation is an act of delineating or segmenting pathway of interest. And Tractometry is an attempt to quantify the bundle reconstruction that we just performed at a population level or for a group comparison. So all of these steps are different way of using diffusion MRI. So some people specialize in one of these steps or a few of them. So if you have different questions, it's important to ask the right person. So that's why during the presentation, I will try to point toward the right speaker for each small overview. So the first important thing to consider for diffusion MRI is the acquisition itself. So most people are familiar with spatial resolution, which is the size of the different voxel that you can have when you do an acquisition, the size of the smallest structure that you can look at in 3D. Diffusion MRI have an extra layer of complexity on top of it. It's angular resolution. So since we want to probe the movement of water in different directions, we have to acquire information about each direction. So here's a small schematic of 6 different directions that we want to probe for the movement of water. So if you don't have enough of these, maybe you won't be able to quantify correctly the microstructure or the local modeling later. So you need to have a proper sampling of the orientation that are possible, and this will limit you for future steps. So if you have existing data that have a certain kind of acquisition, it's important to know the limitation of this acquisition. Or if you are going to acquire data, this is an early decision that will have a big impact later. So I'm sure Ariel and Raphael will have more detail about that in their DTI and DKI talk. Also, Suzy will talk about advance in acquisition and the Connectome 2.0. So if you have questions, probably refer to this speaker, listen to their talk, it's great. So this is for the acquisition. So once you perform that acquisition, one line of analysis for diffusion MRI is microstructure imaging. So the goal of microstructure imaging is to quantify the tissue characteristic and its composition. So if you want to look at values related to average tissue density, cell size, axon diameter, free water contamination, all of these are considered microstructure imaging approach. Each come with a model that have pros and cons. So I'm sure that Raphael will have a lot more detail about that. This week, Raphael is the expert in microstructure. He has talked about DKI and specifically about microstructure modeling. So refer to his talk if you are interested in this thing. But the general idea is always pretty similar. If you want to investigate specific characteristic of the brain tissue, you need to have a simplified model representation. So you represent axon like tube that occupy a certain space. The tube have a different diameter, different thickness. There is a spacing in between to represent the extracellular component. So you have a simplified model that then you can simply extract value from after you perform fitting to the data. So the model needs to fit the data, and then you extract values such as myelin volume fraction, axon volume fraction, or G ratio, which is relationship between the inner and outer diameter of an axon. So you end up with scalar map like these that quantify the underlying tissue composition. So that's an approach for diffusion MRI, microstructure imaging. So another approach is the line of tractography, which is that take a lot more step to get to. So if you want to take this approach, so local tractography, one of the first thing you have to decide is about how you will represent the way fiber are oriented in the brain. So if you want to do tractography, you first have to do local modeling. Local modeling is a very simple concept. At first, you just have to represent all the crossing or the straight line or the curve or the fanning are locally oriented. So this is a small example where you have an X-shaped crossing right here. If you have a simple model like DTI, diffusion tensor imaging, you end up representing the straight line and the crossing as a single object, like a sphere or a small ellipsoid like this. So in the straight line, the ellipsoid is quite good. The ellipsoid represents the average orientation, but when you reach the crossing, you end up with a 45-degree angle that is like, it's basically wrong for both pathway. So this is a local model that does not handle well the crossing, for example. But then you have more advanced models that are available if you have the right kind of acquisition that allow you to better represent the crossing. So this is an ODF, orientation distribution function. This is a FODF, fiber orientation distribution function that allow you to have a better crossing representation. I'm not going to explain any of these. I'm sure Ariel and Raphael will talk a lot more about local modeling in their DTI and DKI, diffusion tensor imaging and diffusion kurtosis imaging talk. Also, Maxime will talk about more advanced, like this one, more advanced local model, and he's talk about RD model or spherical harmonics. So if you have questions or are particularly interested in local modeling, I suggest those talk or asking questions to these people. Then once you have the local model, you can perform tractography. So tractography is also very intuitive in terms of concept. The specifics of it is more complicated, but conceptually it's simply connecting the dots between local models. So if you have a small local orientation, like here it's represented as a single peak per voxel, and you want to know how things are connected. It's really intuitive to just connect the dot. Your brain is doing it right now. You feel like this is a smooth vector field that just merge into one. And this is an anatomical drawing from more than a century ago that showed approximately the same structure. So you can see here that this is connecting to this and it's smoothly merging into one thing right there. It's kind of the same that you can see here. So this is very like visually intuitive, but the complex detail that are emerging from tractography will be explored in more detail by Gabriel in his tractography talk. So I recommend this talk if you are interested about tractography. What is interesting is that all of the specific of the algorithm, the size of the step, the number of steps, how do you stop, is a lot of fine-tuning, but overall the idea is simply to reconstruct probable pathway. So if you start a line from a certain point, will it go this way, this way? If you fine-tune the parameter or change the algorithm, it will change the result, but the idea is to reconstruct probable pathway based on the local model. So I recommend this talk for the specifics of tractography. Then once you have a tractogram, which is the union of millions and millions of lines that represent probable path, that's a tractogram. So once you have a tractogram, you cannot just analyze like the whole thing at once by looking at it. So one approach to analyze it is connectomics. So if you want to investigate the global connectivity of the brain, Connectomics is for you. If you simply have those lines, that's not enough. You need to have a cortical parcellation. So basically a way to subdivide the cortex or the nuclei into multiple regions. And then you say, how is region A connecting to region B? How many lines are connecting region A and region C? And once you have this information, you can put it into a simplified representation, which we call a connectivity matrix, that basically summarize this whole tractogram and this parcellation into a 2D array with value in it that count various values. So if you are interested about connectomics, I recommend the talk by Etienne about connectivity. So the way you can interpret this, you can compare this using correlation, distance between matrix to compare group. So this is a very interesting approach to tractography quantification. Another approach, so this is a kind of a parallel branch of analysis. If you have strong anatomical prior, so you know that you're studying a pathology related to the corticospinal tract, you don't want to look at the global connectivity of the brain using connectomics, but you want to look at the bundle itself. You can use bundle segmentation. So bundle segmentation typically use anatomical landmark or shape as a way to isolate a bundle of interest. So in the small GIF that you can see on the right, it's the process of manual segmentation, so virtual dissection. So you can say like corticospinal tract should start in the brainstem, should finish in the precentral gyrus, should go through an internal capsule, and then you just perform a manual segmentation. So you manually identify the streamline that you like, that are related to the pathway of interest. This is manual, it takes a lot of time, it's cumbersome, like not everyone would like to do that on 1,000 subjects. So this is why Eleftherios will introduce Rheault bundle in his automatic segmentation talk later this week, which is an automatic way of obtaining various bundle. So this way you have a bundle of interest that will bring you some sense of shape of the streamline that are interesting to you, but how do you compare it? How do you quantify it, and how do you do group comparison, for example? So this is done using Tractometry. So a bundle segmentation is not an end by itself. It needs to be quantified using Tractometry. Before I introduce the small concept of Tractometry, it's important to know that bundle by themselves for n equal 1, so a single individual, it can be useful. So in the case of surgery, deep brain stimulation, it can be useful to have access to a streamline and look at the shape, the way it curves, it gets pushed or deformed or disrupted. In a single individual, it can be useful. So for example, in this case, you can see that this is the inferior fronto-occipital fasciculus. It seems to have been pushed by a tumor, pushed inward. So this could help a surgeon to say, like, should I enter like from the side or from the top? You have to look at more than one bundle to see, like, does it disrupt something important? Does it disrupt the network of visual or oral scale, stuff like this could be important at the individual level. This is another example where there is a tumor that is kind of lodged inside of the optic radiation. So it's pushed inside of the curve, and the bundle seems quite symmetrical. It seems complete and in the right place. So you could say, maybe this is still working. Maybe this is still viable. So this will impact the decision of the surgeon, or maybe not, like he is the surgeon, he decides. But it's important to know that for an individual, bundle segmentation can be useful. But if you have a large population with thousands of subjects and you want to compare group A to group B, does the language network change? For example, you have to do tractometry. So there is a bundle analytic framework in DIPY that will be introduced later this week. Ariel will also talk about sparse group LASO and AFQ and various ways of doing large group population comparison. And also, this is important to remember, because if you want to simply compare a bundle, you can just say the volume of the bundle at time point A change at time point B. That's a way of doing comparison. But tractometry is a bit more advanced, where you actually split the bundle into tens of subsections, and you can say the change is actually happening at the front, at the back, or in the core. And this is very interesting because it can allow you to have insight into the anatomy and how the brain is actually changing over time or changing with pathology. So if you're interested in tractometry and quantification of bundle, I recommend these talk and to talk to these speaker this week. So this was a brief overview of the themes that are relevant to the DIPY workshop and what the speaker will talk about this week. If you have specific questions, maybe refer to these people or listen to their talk if you're interested in that subject. So I hope this helped you to have some sense of processing, ordering, or the context of the various subjects that we present this week. If you have any question, I hope I can help. Thank you.